Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our playlist Basic Electrical Engineering and Class 12th Physics, in our chapter Alternating Current Circuits, we'll explain application of phasor representation. After introduction and core practice of phasor representation, in this application part of phasor representation we'll understand how phasor representation makes summation difference of alternating quantities quite convenient and fast, and we'll also learn how the same phasor representation can be used for the multiplication or division calculation in alternating quantities. So let's start application of phasor representation. To represent sinusoidal quantities and to analyze alternating current circuits, a simple, convenient and direct method known as phasor representation is introduced by C.P. Steinmetz. According to phasor concept, phasor is a rotating vector with its scaled length equivalent to magnitude of sinusoidal quantity and its angular velocity of rotation in anti-clockwise direction equivalent to angular frequency of sinusoidal signal, and as it rotates, its projection on vertical axis represent instantaneous magnitude of sinusoidal quantity, and with time phasor continuously rotate with constant angular velocity and its projection on vertical axis represent time varying sinusoidal alternating signal. This is exponential relation of phasor representation where Vm represent amplitude or magnitude of sinusoidal signal. This e raised to power j omega t represent rotating nature of phasor, and in this e raised to power j0, this 0 represent t0 instantaneous phase of sinusoidal quantity and a standard reference sinusoidal voltage having instantaneous value 0 at t equal to 0 represented by standard V equal to Vm sin omega t. Trigonometric expression is represented by a rotating vector of scaled length equal to magnitude or amplitude of voltage Vm, and its t0 position makes an angle 0 degree equivalent to phase of sinusoidal quantity from horizontal reference, and t0 instantaneous magnitude, the projection of this rotating vector is 0, and as it rotate by say 30 degree, its vertical projection become half of amplitude. At 60 degree it become root 3 by 2 times of peak amplitude, and at 90 degree rotation position the projection on vertical axis become peak amplitude magnitude, and further rotation reduce instantaneous magnitude that becomes 0 after half cycle, and change polarity become maximum in opposite direction and then reduce and become 0. So one cycle of rotation of this rotating vector generate one cycle of alteration. So this line representation and this wave diagram represent this trigonometric expression or this exponential relation. If a sinusoidal signal starts from positive peak instantaneous value at t equal to 0, this corresponding to 90 degree phase condition on standard reference wave, then this sinusoidal alteration represented by this trigonometric expression can be represented in phasor exponential form as shown in this yellow highlight as Vm e raised to power j omega t e raised to power j90, where Vm represent magnitude of phasor, this 90 represent phase angle or initial position of phasor from horizontal reference, which is plus 90 degree means 90 degree in anticlockwise direction, and this e raised to power j omega t represent variation of phasor position from horizontal reference with time or rotation of phasor. At t equal to 0, position of phasor represent vertical axis projection positive peak instantaneous value, and a 60 degree rotation will reduce vertical axis projection half of peak magnitude. 90 degree rotation position results as 0 instantaneous value. Now voltage change polarity increase in opposite direction. At 4, the position of phasor represent instantaneous magnitude on projection of vertical axis. At time instant 5, phasor represent negative peak instantaneous magnitude as its projection on vertical axis, and rotation at position 6, 7 and 8 represent corresponding instantaneous magnitudes, and one cyclic rotation generate one cycle of alteration. Similarly, when a sinusoidal voltage starts with negative peak instantaneous magnitude at t equal to 0, then its phase angle is treated as minus 90 degree and its exponential phasor representation represent phase as minus 90 degree here, and we'll draw a phasor of scale length peak magnitude Vm and its initial t0 position with horizontal reference is minus 90 degree. Minus means it is in clockwise direction and it makes clockwise 90 degree angular position as shown here, and its projection on vertical axis represent t0 initial value. Rotation of phasor in anti-clockwise direction after quarter cycle bring 0 instantaneous magnitude. Half cycle will produce positive peak instantaneous magnitude as projection on vertical axis, and one complete rotation of phasor generate one cyclic alteration on vertical axis projection as represented here. Phasors are complex quantities and which may be represented in exponential notation or in phasor diagram. This multiplier A represent magnitude or scaled length of phasor, and it may be maximum value or amplitude of sinusoidal signal, or it may be RMS value of sinusoidal signal. This e raised to power j omega t represent rotating nature of phasor, and all phasor concerned in one study got the same angular frequency or same angular velocity of rotation in anti-clockwise direction. So this become a common feature for all phasor, and generally in phasor representation this common quantity is not mentioned in phasor expression, as this become phasor representation with magnitude and angle. This theta represent phase angle of sinusoidal alternating quantity or represent t0 instantaneous magnitude. Now e raised to power j theta representation can also be written as magnitude angle form, and this format is known as polar representation, and it represents that from origin there is a scaled length of a magnitude and that makes an angle theta with horizontal reference line. Now this polar expression of phasor can be represented as two right angle axis components. This a with angle theta on horizontal line produce a component a cos theta, and on vertical line it produce a component a sin theta. Now this horizontal component is known as real or active component, and this vertical component is known as imaginary or reactive component, and this imaginary or reactive component is differentiated with J notation, and this real horizontal active component and vertical imaginary reactive component format is known as rectangle format. Now simple mathematics can convert polar to rectangle or rectangle format to polar format. In this phasor representation, this magnitude angle format is known as polar format, and this horizontal real active component and vertical imaginary reactive component format ax plus jay is rectangle format. And if one know magnitude and angle polar format of phasor, then he can find out real component as a cos theta and imaginary component as a sin theta. And if one knows rectangle form, real component and imaginary component ax and ay, then from this right angle triangle using Pythagoras one can find out magnitude of polar form and angle of polar form by these two yellow highlight relation. And one can say we have one trigonometric relation and one Pythagoras relation, and out of four, magnitude, angle, real component, imaginary component, any two is known to you, you can find out other two. Addition or subtraction of sinusoidal quantity in phasor representation become very simple in Cartesian coordinate form or rectangle form, and for that the polar magnitude and angle are decomposed into two real horizontal active component ax as a cos theta and vertical imaginary or reactive component as a sin theta. And for summation or subtraction, we'll calculate all real component together, all imaginary component together, and finally the resultant real and imaginary components using Pythagoras will give us magnitude of sinusoidal result, and trigonometry application in this right angle triangle gives us phase angle of resultant sinusoidal quantity. Phasors are in fact rotating vector, but for analysis the rotation is frozen, and that frozen state of phasor becomes simply vector, And for addition and subtraction, the phasors are analyzed in rectangle form. Suppose we have to make addition and subtraction of two phasor E1 and E2, then both E1 and E2 are written in rectangle format. Here this blue phasor E1 got a real component small a1 and vertical component small b1. Similarly, this black E2 phasor got real component a2 and imaginary component b2. And for addition, phasor addition become a simple vector addition, and as per parallelogram of forces, the tail of this E2 phasor or E2 vector is put on the head of E1, and tail of E1 and head of E2 when connected, this diagonal of parallelogram gives us the summation vector E as E1 plus E2. Similarly, to find out difference, E2 is reverted and made minus E2, and now this minus E2 is added to E1 again by parallelogram principle. The tail of minus E2 is placed on head of E1, and tail of E1 and head of E2 are connected together to get E1 minus E2 phasor. To find out sum of two or more phasors, phasor are represented in rectangle form, and now addition in rectangle form is done such that real part of first phasor small a1 is added to real part of second phasor. Similarly, imaginary or vertical component of two phasor are added together to get resultant real component of some phasor and resultant vertical component of some phasor. And this is also true from this phasor diagram. This a1 is real component of E1 phasor, and this a2 is real component of E2 phasor, and this a1 plus a2 become real component of resultant sum phasor. Similarly, this b1 is imaginary component of E1, and this b2 is imaginary component of E2, and this b1 plus b2 become imaginary component of resultant vector. And if we use Pythagoras theorem, then magnitude of some vector can be obtained by Pythagoras calculation of base and perpendicular, and hypotenuse is square root of base square plus perpendicular square. And similarly, we can find out phase angle of resultant Brown phasor, which is sum of E1 plus E2, as tan theta is perpendicular upon base, and perpendicular is b1 plus b2 and base is a1 plus a2. So this trigonometric expression will give us angle, and this Pythagoras will give us magnitude, and this magnitude angle format become the resultant vector sum of E1 and E2, that is E. And usually the final answer is written in polar format only. Here we have done this calculation for two phasor E1 and E2, but the same calculation can be made in a similar manner to any number of phasors. The difference of two phasor is also summation with change of sign of second phasor. We have to find out difference of two phasor E1 and E2. So both phasor are obtained in rectangle format, and in rectangle format the difference of E1 and E2 can be obtained as difference of real part together and difference of imaginary part together, and this gives resultant real part and resultant imaginary part. And by Pythagoras calculation we can find out magnitude, and by trigonometry we can find out angle, just like summation. And it is also illustrated here in this phasor diagram. This is E2, and when reverted become minus E2, and in E1 minus E2 is added to give E1 minus E2 phasor. And now the real part of resultant phasor is the difference of real part of first phasor and real part of second phasor. So A1 minus A2 is real part of resultant phasor. Similarly, the difference of imaginary part B1 of first phasor and B2 of second phasor gives us imaginary part of resultant, and since B2 is greater than B1 in this case, then vertical part become negative. So our resultant phasor got its inclination to downside of horizontal line, so its angle comes as negative. This numerical example will explain the concept and clear all our doubts regarding summation or subtraction of alternating quantities. We are given three alternating current, all of same frequency but of different magnitude and different phase conditions, and we have to perform addition as well as subtraction to find out resultant current of these three given currents with trigonometric expression as 8 sin 200t plus 30 degree, 7 sin 200t minus 60 degree, and 4 sine 200t minus 45 degree. Now for phasor method, we can express those sinusoidal signal in polar forms with magnitude and phase angle. So the magnitude of first sinusoidal current is 8 ampere and its phase angle is plus 30 degree. The second current is 7 ampere in magnitude with minus 60 degree phase angle, and third current is 4 ampere in amplitude and minus 45 degree phase angle. Now we have to make addition as well as subtraction among these three currents. We know for addition and subtraction we need rectangle format or Cartesian coordinate form. So this first current of amplitude 8 and angle 30 degree in polar form is converted into rectangle form with horizontal real active component as 8 cos 30 and vertical imaginary or reactive component with J notation as 8 sin 30. Similarly, magnitude 7 ampere and phase angle minus 60 degree current can be converted in rectangle form with horizontal active component. Real part of this is 7 cos minus 60 degree and imaginary vertical or reactive component with J notation is 7 sin minus 60 degree, and for 4 angle minus 45 degree real active component or horizontal component is 4 cos minus 45 degree and imaginary vertical reactive component is 4 sin minus 45 degree with J notation. Now for this summation or subtraction calculation, subtraction is also a summation with sign change. We'll add all active component together and we'll add all reactive component together. The value of cos 30 is 0.866, sin 30 is 0.5, cos minus 60 is plus 0.5 and sin minus 60 is minus 0.866. Cos minus 45 is plus 0.707 and sin minus 45 is minus 0.707 with multiplication of respective amplitude. All three real part shown in green highlight are added together with sign convention and it comes as only 0.6. Similarly, the remaining reactive or J component or vertical component is added together and it comes as J 7.234. Now this rectangle format of resultant current can be converted into polar form where magnitude is obtained by Pythagoras calculation of horizontal component and vertical component, and square root of base square and perpendicular square gives us magnitude 7.26 ampere, and its phase angle can be obtained as tan theta is equal to perpendicular or vertical component divided by base or horizontal component, and tan inverse of that gives us angle 85.256 degree. So this resultant current I got a magnitude or amplitude 7.26 ampere, and with same frequency it got a phase angle of plus 85.256 degree. So this would become our resultant current. For multiplication and division among phasors, we have to use polar coordinates as it become very convenient and simple, and in polar coordinates we have to represent phasor in terms of its magnitude and phase angle, and the simple format is magnitude angle theta. Now when we have to perform multiplication among several phasors, then magnitude of individual phasors are multiplied together to get magnitude of resultant multiplication, and the phase angle can be obtained by summation of individual phase angles, as we have given two phasor, one of amplitude 10 angle 30 degree and second of amplitude 4 and angle 45, and for multiplication the individual amplitude get multiplied, 10 multiplied with 4 become 40. So this 40 is amplitude of this multiplication, and angle will get added as exponential power and this become 75 degree. So the product of these two phasor got a phase angle of 75 degree. So it's simple, magnitude get multiplied and angle get added. Similarly, for division among two phasors, the magnitude of two phasors get divided from each other, and the resultant angle of division would be the difference of phase angle of two phasors, as we have to divide 4 angle 45 phasor from 10 angle 30 phasor. So this in this division magnitude get divided and 10 divided by 4 become 2.5, and angle will subtract, and when we subtract 45 degree from 30 degree it become minus 15 degree. In alternate convenient format, tan angle 30 when divided by 4 angle 45 magnitude get divided one by another and result is 2.5 when 10 divided by 4 and angle when subtracted become minus 15 degree. So this would be our result of division among two phasor. We hope just like other two learning video of phasor representation, this application part of phasor representation has explained all related aspect of phasor representation. Now you know for addition or subtraction one has to use rectangle form of phasor, and for multiplication and division one can use polar form, and mathematical analysis become quite convenient. Our other learning video of the same playlist are equally useful. You can use them in your studies or refer them to your friends. And if you need exam centric dedicated notes of expert teacher or online doubt clearing classes, do join our YouTube membership. Happy learning. Have a nice time. Thank you very much.